and ask questions.
Yeah, so welcome everybody to today's Quasiworld seminar. So our first speaker is Juliana Xavier. I hope I'm pronouncing this correctly. And she will tell us about the indecomposability of Julia sets from the topological viewpoint. So please, Juliana.
Thanks so much. I am very glad to be speaking here. It's quite the honor, really. And well, I wanted to say that I don't work in complex dynamics. I specialize in low-dimensional topological dynamics. And I came across this problem of indecomposability of Julia sets, studying another problem of existence of periodic orbits for sphere endomorphisms, really. So, like, the aim of this talk is to explain, like, how these two problems relate. And well, so first part is this question is, does there exist a rational function f from the sphere to itself whose Julia set is an indecomposable continuum? So this is an open question, and it's like the motivation for this talk. I will just put a slide with the definition. A continuum is a compact and connected set, and it is indecomposable if it is not the union of two proper subcontinua, meaning that if you write the set as the union of other two continua, then one of them is necessarily the whole set K. So you cannot decompose it as the union of two subcontinua. So the first examples that come to mind are always decomposable. Let me see if this works. You see this pointer?
Yes.
Okay. First examples are always decomposable. Of course, a segment, you can take two subsegments and you have a decomposition. Same with the circle. But even taking a non-locally connected, like this one here, the topology sine curve, you can take this first part here as the set A, and then the other subcontinuum as the set B for a decomposition. What certainly you can't do is take like this part as one of the sets for the decomposition, because then the complement, if you take the closure of the complement, gives you the whole space. So this gives a hint, like if you want to construct an indecomposable continuum, you really have to have, like, everything is accumulating everywhere else, some sort of things like this. And well, here I have an actual picture of an indecomposable continuum. So what is this picture is known as the Wada Lake example, that you have four regions, four complementary regions, like 1, 2, 3, and 4 here. It's a plane continuum that is the common boundary of four disjoint open disks, right? Yeah, so there is four disjoint open sets in the plane that share a common boundary. And this object here, the indecomposable continuum is the boundary here. It appears dynamically. I will explain this example later on, but it is known as the Plikin attractor, where you put in each of these complementary regions, you put a repeller. You have a repelling fixed point, and the continuum is the boundary of this thing. But it's an invertible map. It's a sphere diffeomorphism. So it appears dynamically, but in an invertible context.
So I have a quick question.
Yeah.
Why is this actually indecomposable?
Oh, it is not easy to prove. It's not straightforward, really, to prove that any continuum is indecomposable. But in this case, what you can prove is that if you take 3 points any of 3 points, and you take the minimum continuum that connects 2 of them contains the other. This is equivalent to decomposability, and in this case, you can show this because of the dynamical properties, like the composants would be the unstable manifolds of the points, and in this way you can show that.
Oh, okay, thank you.
But there's work to be done. You can, by looking at it, you can feel like it is indecomposable, because whenever you try a decomposition, you cannot do it, but you can prove it like with some equivalence of indecomposability. I have a different example here, which is the pseudo-circle. How you construct this one is like you take this outer chain of disks, you take a circular chain of topological 2 disks, and you put inside exactly the same. It is also a circular chain of topological 2 disks, but in a way that is crooked in the previous one, meaning that, for instance, if you want to get from here to here, like you want to skip 2 of the disks, you cannot do it in a straightforward manner. I mean, you have to go here, then visit a previous disk, and then go here. Like this is what is called a crooked chain. You put it in the previous one in a crooked manner, and of course you do this inductively. Now I will put another chain in this small chain that is crooked in this one, and in the limit you will get an indecomposable continuum. Also not easy to prove, but it's all work done. And why I put this example here is because this one, it admits a non-invertible dynamics, meaning that it double covers itself, like if it were a circle, that of course is not, but it double covers itself. The problem with this, I don't know, it's this double covering, we do not know how to extend it to a branched covering of the sphere, okay? So it double covers intrinsically itself. You have a double covering of the pseudo-circle to itself, but we don't know how to extend it to a branched covering of the sphere or, yeah, the annulus. Here I have, this is the conformal dynamics problem list by Bielefeld. It goes back to the late 80s. And I think this problem goes back to here. It has, the first section is about local connectivity of Julia sets. And I highlighted here question 2, which is give a plausible topological model for the Julia set of a Kremer polynomial. Well, it is known that there are polynomials whose Julia set is non-locally connected. It's the so-called Kremer polynomial. So there are known examples of these things, but it is unknown yet up to now what is the topological structure of this Julia set is. So how badly non-locally connected can they be? Like, maybe is it possible that they are indecomposable continua? For example, if you take a look at this picture where you have a point that is B-accessible, like you have two different external rays landing at this point, this of course induces a decomposition of the Julia set. So for an indecomposable Julia set, this would be impossible to have the accessible point. But this is it's also an open question whether or not Kremer polynomials can have the accessible points. So the following question we are interested in is it possible for a branched covering of the sphere? What I mean here is maybe a rational function is to reach an object, but for a branched covering, just continuous map, non-invertible, maybe we can construct indecomposable continuum that is totally invariant. That would be the analog of the Julia set. I have the more precise question here. Does there exist a branched covering of the sphere supporting a totally invariant indecomposable continuum? Well, the answer is yes for this one. We gave an example in 2023. I will take a moment here to present my co-workers. They are Jorge Iglesias, Aldo Portela, and Álvaro Robela. We are all working in Montevideo, in Uruguay. And it has been years that we have been interested in non-invertible surface dynamics, topological dynamics. So the answer is yes. I would like to explain the construction, but our map is not Thurston equivalent to a rational function. This is like bad news because we wanted a plausible topological model for a indecomposable continuum Julia set, and the example, even if it supports an indecomposable continuum that is totally invariant, it fails to be even Thurston equivalent, which is very light equivalence. It fails to be Thurston equivalent to a rational function. So I will explain the construction. Before giving the example, I also note that we don't know how to do it for a topological polynomial. A topological polynomial would be having a simply connected totally invariant region, as the basin of attraction of infinity would be in the rational case. We don't know how to do this. Our example, in fact, is a parabolic 2-2-2-2 orbifold. Well, so I will explain the example now. I don't know if you have questions.
A quick question. Will you also explain the connection of the continuum with the Thurston obstruction?
Oh, sorry, again?
I mean, you said that your map that you...
Yes, I will explain why it is not, yes.
Okay.
I will explain why it is not Thurston equivalent to a rational function.
Thanks.
Yeah, sure. The example inspires on what is known as the derived from Anosov diffeomorphism. So I will explain that one first. It is well known, but anyhow. So you take hyperbolic toral automorphism of the two torus, like this one, and what you do is take a fixed saddle, like so, and I will perform a local perturbation. I'm only changing the map here in the neighborhood of this saddle fixed point. And the perturbation is what is drawn here. So I replace the saddle fixed point by an attracting fixed point and two saddles. It's like I split open the stable manifold and make this perturbation to create an attracting fixed point. When you perform this perturbation, what happens is when you look at the basin of this attracting fixed point, the new fixed point, the new attracting fixed point that you created, it's like an unbounded disk on the torus that is like with an irrational slope, of course, accumulating everywhere. It has local product structure like Cantor times interval here. And so the boundary of this basin of attraction is in fact an indecomposable continuum. So the complement of the basin of attraction of the attracting fixed point is a repelling set that is an indecomposable continuum. Indecomposability again comes from this fact that the composants of the continuum are dense. And in fact, this example, I will go back here, is that example, like hyperbolic toral automorphism projected to the sphere by the double cover, the usual double cover of the torus onto the sphere. So you can perform the perturbation in like 4 fixed points, and then these 4 fixed points, you make it coincide with the critical points of the branched covering of the torus to the sphere, and then you will get, like, it would be like the depleting repeller in this case, where the points here are all attracting. Like I split open the stable manifold, so I made attractors in this case in each one of these bases, of these regions. So that's what I derived from an Nosov diffio is. And so the way to construct the example is, in fact, get the exact same idea, but taking an Nosov endomorphism of the torus. So we take the Nosov endomorphism, which is induced on the torus by this matrix. Any linear endomorphism would work, but it's an example, right? As it is linear, as it is linear, it will project to the sphere, right? And what you get is a Thurston map of degree 2, because it's of the same degree as this one, which is the quotient of a torus, of an Nosov endomorphism of the torus. So this is the first step of the construction. So we're like here. I just wrote the critical portrait here. When you project, you have to make a computation, right? But this one has 2 fixed points, P and Q. And when you project here, the branched coverings of the projection goes, of course, to the postcritical set of the Thurston map induced here. And with this critical portrait, like the 2 critical points go to critical value and then to a fixed point. So what we are going to do now is at each of these ones, this fixed point here, perform the derived from an Nosov perturbation to create an attractor. So I will replace these fixed points P and Q for attractors, right, to create attracting fixed points. I have the picture here of what that would do. Now the basing of attraction would go around everywhere, like in the derived from an Nosov example. And you see here, when you take a pre-image, and the critical pre-image will open 2 arms, like so. And in fact, this is an example with infinitely many Wada lakes, because of course you will have pre-images of these things all around. It's everything is accumulating on everything, so this one's more accurate, but still a bad drawing. But what this accomplishes, doing the derived from an Nosov perturbation in this example, is exactly a total invariant indecomposable continuum for a branched covering of the sphere. That, again, we don't know how to do it, like having a total invariant simply connected region. Like for a topological polynomial, we still don't know how to do this. And here it's what you were asking me. It is a theorem of Thurston that a parabolic 2-to-2 orbifold is Thurston equivalent to a rational function if and only if the associated matrix is either expanding or has complex eigenvalues. In this case, of course, the associated matrix is an also the matrix that is induced in fundamental group of the torus is an also. So it is not Thornton equivalent to a rational function. That's the reason. I don't know if there are questions.
No, go ahead.
Okay. So part 2 is really like how we came across this problem. It's what's called the growth rate inequality. This is a conjecture of Mike Shu that if you have a sphere map of degree D greater than 1, I mean a non-invertible map that is C1, then the following inequality should verify, like lim sup when n goes to infinity of 1 over n log of the number of fixed points of Fn should be greater or equal than log D. It's like these sphere C1 maps should have an exponential growth rate of periodic points. It is what happens for a map of the circle, right? If you have a circle map which has degree D, you will have at least D-1 fixed points here, because if you take a look at the graph, here is depicted a degree 3 map of the circle because it goes around 3 times. You will have 2 fixed points. It's the minimum number, and even if in the topological context, you don't need C1 hypothesis here. You will always have at least D-1 fixed points. And in particular, Fn will have at least Dn-1 fixed point, which would give this rate. If this is Dn of the order of Dn, you will have this verified. So this is a really elementary question about sphere maps, about the number of periodic points sphere endomorphism should have. I would take a moment now to explain why the C1 hypothesis is put here. It's because it is not true in general for sphere maps. And here is an example. I'm looking at the sphere as the plane with a point at infinity, and I put polar coordinates, and I'm making 2 times the modulus and twice the angle. So of course, this map, every point is increasing its radius, so it has no periodic points other than 0 and infinity, and so it doesn't verify this growth rate inequalities. Only for every period, there is just 2 periodic points, and every other point is like 1 point. But this map is not C1, right? You have at 0 here, like a repelling fixed point, and critical points in the C1 context should be attractive. So that's why it's C1 hypothesis in the conjecture. It is in fact an infinity-infinity orbifold, and parabolic orbifolds are known to verify the growth rate inequality if their signature is other than infinity-infinity. This is also a theorem of ours. And also C1 infinity-infinity orbifolds verify the growth rate inequality. When you have an infinity-infinity orbifold, and the map is C1, these critical points are attracting, and then you can check for periodic points in the complement of the basin of attraction of these points, which is an essential set in an annulus. This our first work as a group was to develop the theory of annulus endomorphism, and very much focusing in this growth rate inequality. And in particular, if you have an essential set, invariant set in an annulus, you have all the periodic points you need there. Also interesting is that infinity orbitals may fail to verify the growth rate inequality, even if they have a compact invariant set. Yeah, why I'm saying this is because you can look at this example and think that it's someone artificial because you're losing the periodic points because everybody's wondering and you have no recurrence whatsoever. But in fact, you can make an example of annulus endomorphism, which has a compact invariant set and has no periodic points. I will explain this here. So what I'm trying to explain here is an example of a sphere branched covering or an annulus covering in this case that has a compact invariant set but has no periodic points. I mean, if you look it in the sphere, no periodic points other than 0 and infinity, like the first example, but this one has a compact invariant set. So the map, I will give it again in polar coordinates. And the first coordinate is a function of the two variables, and the second coordinate depends only on the angle. So I'm going to describe the angle map first. So it's a degree 2 map of the circle that has a compact invariant set without periodic points. So this is the first thing you have to think about, that you can make a circle map of degree 2 that has a compact invariant set without periodic points. There are several ways to do this. One can do it like combinatorially, or also like a high degree Denchois type of example, but I will admit that this exists for the purposes of this example. So I take a circle map that has a compact invariant set without periodic points. And then the other map, I write it like this, is phi of r, that is this function of the radius, like has a fixed point at radius 1, and every other point increases its radius. And then the formula for this first coordinate map is this phi of r plus r times the distance of the angle to the compact invariant set. So if I take a look now at this map of the annulus, I have that this set here, radius 1 times the compact set k, is an invariant set, because phi fixes this one, and when the angle is in the compact set, this is 0, so these points are invariant under the map F. But what this does, this formula here does, is that if you take an angle that is not in the compact set, like this fine line here, every point will increase its radius. So it goes to infinity and it's not periodic. And in the other angles that do belong to the set K, they will be stopped here at 1, so this point will go to the other one at the same radius, but every other point will increase its radius also. So like you have destroyed all the possibility for periodic points, and there you have, it's an annulus covering, which has a compact invariant set, but no periodic points whatsoever. Of course, it also fails to be C1 for the same reason, that you have repelling critical point here. Well, for topological polynomials, for example, this would be an example of topological polynomial. I just want to have a simply connected, in the sphere, simply connected region that is totally invariant. So topological polynomial is a branch covering non-invertible, and we assume that there exists a simply connected region that is totally invariant. So this is a hypothesis we put so that we have somewhere to look for the periodic orbits we are looking for. Remember that whenever we have a map like this, we are interested in the growth rate of periodic orbits. So having a totally invariant set, a totally invariant region like this one, like mimic the basin of attraction of infinity in the rational case, gives us somewhere to look for. Then one may look for periodic points at the boundary of the region. And the thing is that if the boundary is locally connected, then this works. Meaning that we have this theorem that if you have a branched covering of degree d of the sphere, assume that there exists a completely invariant, simply connected region whose boundary component is locally connected. Assume, moreover, that it is not the case that there exists only one critical point in the boundary of R that has multiplicity d minus 1 and is fixed by f, which is exactly the counterexample case, right? That the boundary of this region is exactly one critical point carrying the whole multiplicity. Then f has the right. F has the right means that it verifies the growth rate inequality. So we can find these periodic points if, here is the important hypothesis, if the boundary is locally connected. This is merely a technical assumption. I mean, we believe it's true whether or not the boundary is locally connected. The thing is that we are unable to prove it, but yes, so I will explain why this make it work. So like the proof, it's an idea of the proof, but Riemann theory applied to this region gives a covering map F tilde of the circle, and therefore at least dn minus 1 fixed points of this circle map, the circle map that is acting on prime ends. But if the boundary is locally connected, the boundary of the region is locally connected, then to each periodic point of F tilde corresponds a periodic point of f restricted to the boundary. Note, however, that this correspondence is not injective, as several rays may be landing at the same point in the boundary of R. So yes, here is an example. So you make this prime end compactification of your region. You have a circle covering, and you have all the periodic points of the circle map. The problem is that when you project them to your original problem, there are several of these periodic points that get identified. Here is an example. For example, here the map on prime ends is C squared, and you have three orbits of period three different orbits that are landing on the same point. So you have it's a problem of counting now, because what you want is the growth rate inequality. So you want to ensure that this problem doesn't make you lose a lot of periodic points. So when this sphere branched covering, that is a topological polynomial, has locally connected boundary, you have at least the candidates for periodic orbits, and it's just a matter of counting them, counting that you don't lose so many that the growth rate inequality fails. That is what is achieved really is in this theorem, right? You have to prove that with this identification you don't lose so many. But it's true. So it works. In the locally connected case, it works. You don't lose so many periodic points. So the real problem is when you don't have a locally connected boundary, right? That in a way is this problem that you also don't know examples. It's so much more difficult to work when you don't have examples of the problem you're treating. So what if the impression of a periodic prime end is not a point? If the boundary of the region is not locally connected, certainly is what this happens. The impression of a periodic prime end is not a point. If your map restricted to the impression is injective, that it may well happen that the impression of a prime end is not a point, but is still contained in an injectivity domain of your map, then one may use Cartwright-Littlewood's theorem to find fixed points inside this impression, right? Once you have the compact invariant set in an injectivity domain of your map, there is a whole fixed point theory for surface homeomorphism that can come to help so that you can find your periodic points there.
So sorry, a quick question.
Yeah.
So what is the Cartwright-Littlewood theorem?
Oh, okay. I don't have it written, but I will tell you, right? If you have an orientation preserving homeomorphism, plane homeomorphism, that preserves a compact set, have a compact invariant set that is non-separating, then there are fixed points of the map. This is true in general, it's Brouwer's fixed point theorem. If you have any compact invariant set, you have a fixed point, but Cartwright-Littlewood's is that if the set is non-separating, you can find the point inside the compact set. There is a fixed point inside the compact set.
Okay.
Right? And why you need this? Because you want to apply theory for homeomorphisms, but your map is not a homeomorphism. So you want to change it outside. So you will modify it so that it coincides with your map in the compact set, but outside it's a homeomorphism. So it's another story. So you will have, by Cartwright-Littlewood's theorem or by Brouwer's theorem, you will have a fixed point, but you need to be sure that it's in the compact set, because if it's outside, you have perturbed your map. That's why you need this version, finer version, that the fixed point is in the compact set, okay?
Yeah, thanks.
Okay. The thing with plane homeomorphism is that the theory of fixed point is highly developed. It's really well understood. And for example, in the plane homeomorphism case, any kind of recurrence implies the existence of a fixed point. This is Brouwer's theory. So any kind of recurrence, compact invariant set, recurrent point, anything would give you a fixed point. I put, even then the counting is problematic. Even if you could manage to find fixed points in the impression, remember that you have to count where if this impression would would have two different prime ends will have the same impression, you have to count that this doesn't happen so often. And we also use local connectivity to prove this, that I didn't talk about this, but local connectivity is also used for counting, for the counting part of that theorem. So even then the counting is problematic. But what is more problematic, the real issue here is what if you keep having that the impression of a prime end is the whole boundary of the region, which is what would happen for indecomposable continuum. So this is how these two problems link, right? The one of finding periodic points for sphere endomorphism, and the one of indecomposability of totally invariant continua for surface endomorphism. If this example exists, that we don't know because we don't have examples of topological polynomials whose boundaries are indecomposable continua, but if this were to happen, the technique that we have, the prime end usual technique that we have to find periodic points would fail like catastrophically, because all impressions would be the whole set, so you gain nothing by this, right? So it's the real problem in trying to generalize this theorem and to drop the locally connected assumption. You really need to understand like the dynamics, the intrinsic dynamics in the composable continuum, because what is coming from external rays gives really no information. So what we are trying now, we are working, it's work in progress. If the boundary of R contains no indecomposable continua, so getting rid of this really big problem, then the growth rate inequality is verified. This is very much in progress. It's quite the issue, like when you try to find fixed points intrinsically in continua. It's also a very old problem in topological dynamics, that if you have a continuum, whether or not it has the fixed point property, like if you have a map of a continuum into itself, does it have a fixed point? It's also not known in general, like necessary and sufficient conditions for this one. So yeah, I think that's it. So thanks for the attention.
Oh, thank you. Yeah.